Tuning the network size. Previously, we saw that when the network is too large and has too many free parameters, generalization may not be well. To find the optimal network size, the most common approach is to try many different architectures, train them all on the training set, and choose the one that generalizes best to the validation set. Another approach is to incorporate this structural adaptation into the learning algorithm. There are two ways this can be done. One, in the destructive approach, we start with a large network and gradually remove units and/or connections that are not necessary. Two, in the constructive approach, we start with a small network and gradually add units and/or connections to improve performance. One destructive method is weight decay, where the idea is to remove unnecessary connections. Ideally, to be able to determine whether a unit or connection is necessary, we need to train once with and once without and check the difference in error on a separate validation set. This is costly since it should be done for all combinations of such units connections. Given that a connection is not used if its weight is 0, we give each connection a tendency to decay to 0 so that it disappears unless it is reinforced explicitly to decrease error. For any weight wi in the network, we use the update rule. Delta wi equals to minus eta times delta e differentiated by delta wi minus lambda times wi. This is equivalent to doing gradient descent on the error function with an added penalty term, penalizing networks with many non-zero weights. E prime equals to E plus lambda over 2 times sigma wi squared, summing for all index I. Simpler networks are better generalizers in a hint that we implement by adding a penalty term. Note that we are not saying that simple networks are always better than large networks. We are saying that if we have two networks that have the same training error, the simpler one, namely the one with fewer weights, has a higher probability of better generalizing to the validation set. The effect of the second term in equation 11.32 is like that of a spring that pulls each weight to 0, starting from a value close to 0, unless the actual error gradient is large and causes an update. Due to the second term, the weight will gradually decay to 0. Lambda is the parameter that determines the relative importances of the error on the training set and the complexity due to non-zero parameters, and thus determines the speed of decay. With large lambda, weights will be pulled to 0 no matter what the training error is. With small lambda, there is not much penalty for non-zero weights. Lambda is fine-tuned using cross-validation. Instead of starting from a large network and pruning unnecessary connections or units, one can start from a small network and add units and associated connections should the need arise. In a dynamic node creation, in Ash 1989, the MLP with one hidden layer with one hidden unit is trained, and after convergence, if the error is still high, another hidden unit is added. The incoming weights of the newly added unit and its outgoing weight are initialized randomly and trained with the previously existing weights that are not reinitialized and continue from their previous values. In cascade correlation, each added unit is a new hidden unit in another hidden layer. Every hidden layer has only one unit that is connected to all of the hidden units preceding it and the inputs. The previously existing weights are frozen and are not trained. Only the incoming and outgoing weights of the newly added unit are trained. Dynamic node creation adds a new hidden unit to an existing hidden layer and never adds another hidden layer. Cascade correlation always adds a new hidden layer with a single unit. The ideal constructive method should be able to decide when to introduce a new hidden layer and when to add a unit to an existing layer. This is an open research problem. Incremental algorithms are interesting because they correspond to modifying not only the parameters but also the model structure during learning. We can think of a space defined by the structure of the multilayer perceptron and operators corresponding to adding, removing units or layers to move in this space. Incremental algorithms then do a search in this state space where operators are tried according to some order and accepted or rejected depending on some goodness measure. For example, some combination of complexity and a validation error. Another example would be a setting in polynomial regression, where high order terms are added or removed during training automatically, fitting model complexity and data complexity. As the cost of computation gets lower, such automatic model selection should be a part of the learning process done automatically without any user interference. Figure 11.17. Two examples of constructive algorithms. Dynamic node creation adds a unit to an existing layer, cascade correlation adds each unit as a new hidden layer connected to all the previous layers. Dashed lines denote the newly added unit connections. Bias units weights are omitted for clarity.